Hello everyone. I'm very pleased to introduce our work, titled, Does YOLO Really Need to See Every Training Image in Every Epoch? This work focuses on improving the training efficiency of YOLO series object detectors. YOLO detectors are widely known for their fast inference speed. They are very popular in real-time object detection because they achieve strong accuracy while remaining efficient during deployment. However, we observe an interesting contradiction. Although YOLO is fast at inference, its training process is still surprisingly time-consuming. The main reason is that YOLO usually follows an exhaustive training pipeline. In every epoch, it processes the entire training set. This means that every image participates in forward and backward propagation again and again, even if some images have already been sufficiently learned. This observation motivates our central question: does YOLO really need to see every training image in every epoch? During training, many easy images may already be well learned. Continuing to train on them with the same frequency brings limited benefit but still consumes substantial computation. However, if we simply remove these images, the model may forget previously learned knowledge. Therefore, our goal is to reduce redundant training while preventing forgetting. To address this problem, we propose AFSS, short for Anti-Forgetting Sampling Strategy. The key idea is to dynamically decide which images should be used and which images can be skipped in each epoch. Instead of treating all training images equally, AFSS adjusts the sampling frequency of each image according to its current learning state. The first component is the learning sufficiency metric. For each training image, we use the lower value between detection precision and recall to measure how well this image has been learned. This is important because an image should only be considered well learned when the detector can both classify objects correctly and localize them completely. Based on this metric, AFSS divides training images into three groups: easy, moderate, and hard images. For easy images, the detector already performs well, so repeatedly using them is mostly redundant. AFSS samples only a very small portion of easy images in each epoch. To prevent forgetting, it gives priority to easy images that have not been used for a long time. This mechanism is called continuous review. For moderate images, the detector has learned them partially, but the predictions are not yet fully stable. AFSS applies short-term coverage, which means these images are partially sampled, while recently unused moderate images are prioritized. This helps maintain diversity and training stability. For hard images, AFSS keeps them in every epoch. These images are still challenging for the detector and usually provide more informative learning signals. By always training on hard images, AFSS ensures that the model continues to improve on difficult cases. The final component is state update. AFSS periodically updates the learning sufficiency score and usage record of each image. In this way, the sampling strategy evolves together with the model's learning progress. As training continues, more images become easy or moderate, and AFSS gradually reduces redundant computation. In our experiments, we evaluate AFSS on both natural image detection and remote sensing detection. For natural image benchmarks, we use MS-CoCo 2017 and Pascal-VOC 2007. For remote sensing benchmarks, we use DOTA version 1.0 and DOR-R. We test AFSS on multiple YOLO models, including YOLO 8, YOLO 10, YOLO 11, and YOLO 12, across different model scales. The results show that AFSS consistently accelerates training while maintaining or even improving accuracy. On natural image datasets, AFSS achieves more than 1.43 times training speedup. For example, on MS-CoCo 2017 with YOLO 11s, training time is reduced from 43.9 hours to 28.4 hours, while AP improves from 47.0 to 47.2. On remote sensing datasets, AFSS achieves more than 1.63 times speedup, also with stable or improved MAP. In conclusion, our work shows that YOLO does not need to process every training image in every epoch. Efficient detector training should focus more on informative images instead of mechanically repeating the full dataset. AFSS provides a simple, adaptive, and architecture-agnostic strategy to make YOLO training faster and more effective without modifying the detector structure. Thank you for listening.